Again, we all know that we use clocks and watches to tell time on the earth, and when we travel we reset our watches when we come to another time zone. Let's give ourselves a little problem. Maybe it's about 3 o'clock here in Port Angeles, Washington. What time would it be in Sydney, Australia? In order to answer that problem, let's do some basic geography. There's a line that passes through Greenwich, England, right here. It's called a longitudinal line of 0 degrees, and all time is measured in relationship to that line. 7 time zones to the west is Port Angeles. So let's say it's 3 o'clock here, and we add 7 hours. That means it must be 10 o'clock in Greenwich at this time. Now what about Sydney, Australia? If we look on the globe here, the designation for Sydney, Australia, way around here, is UTC plus 10. We're going to take the time that we now have in Greenwich, England, 10 o'clock, and add 10 more hours. So here's a question. How do we add 10 to 10 on a clock? Because the numbers only go up to 12. And we know that 10 plus 10 is 20. To help us answer this question, let's get organized. We're going to make a clock, and we're going to replace the 12 with 0. Let's point the hand at 3 o'clock where we started, and then we're going to add 7 hours. 1, 2, 3, 4, 5, 6, 7. We arrive at 10 o'clock. Now we're going to add 10 more hours to get to Sydney, Australia. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now we see that the time is 8 o'clock in Sydney, Australia. Here's a complete Mod 12 addition table. You could use it to do additions on the clock. Notice it is a closed set. The identity is 0 and every element has an inverse. Every row and column has a 0. That means that every element has another element in the set, its inverse, which has to make 0 the do-nothing number, the identity. As you experiment with this table, you will learn how to do addition and subtraction, and you'll begin to notice some properties common to all mod systems. The order of addition makes no difference. 3 plus 4 is 7, 4 plus 3 is 7, and so on. So by doing many examples, you will see that there is commutativity in this table. Also, you'll notice that it's closed. All the elements in the table are found in the set. And there's associativity. If you group numbers together, here's an example, you can discover that there's an associative principle. And one last thing, in addition to the identity, which is 0, you will find that every element has an inverse. Once we locate the identity, then we can search for another element that when added to a number gives the identity, the do-nothing number. And here we see that 3 plus 9 is equal to 0. So 3 and 9 are inverses of each other. All mod systems have these 5 important properties. The 12-hour clock system is just an example. It has closure, commutativity, associativity, identity, and every element has an inverse in it. Here's another technique you can use when doing mod addition. Let's do the problem 10 plus 10 and do it in ordinary arithmetic. Now let's take the number 20 and divide by the mod number 12. 12 goes into 20 once, and the remainder is 8. It's this 8 which is the result we're looking for. So 10 plus 10 is equal to 8. The concept we're dealing with here is called congruence. A is congruent to B if, when you divide by the mod number, you get the same remainder. 16 is congruent to 10, mod 2, because when you divide by 2, you get the same remainder. 14 and 26 are both congruent in mod 12 because when you divide them by 12 you get remainder 2. In fact, there's an infinite set of numbers that when you divide by 12 you get remainder 2. Here are just a few of them. We saw earlier that you can add numbers in decimal and then convert to their mod number. Let's look at it from a different way. Suppose we convert each of the numbers to their mod equivalent and then add them. Notice we got 0 as an answer. Now let's try to solve an equation in mod 4. The equation is 5x minus 3 equals 7. Notice the 7 is congruent to 3 in mod 4, and we're going to hunt in the domain 1 up to 30. Trying out the first 6 numbers in the domain results in 2 of them give a true statement. 5 times 2 minus 3 equals 7, equivalent to 3, and 5 times 6 minus 3 is 27. Now we found 2 numbers that make the statement true. What's next? Well, the next one we come across is 10, and if you look carefully you can see an arithmetic sequence developing. And this will be characteristic of all the mod solutions of equations. So there we are. These are the numbers that make that equation true. Now let's see how the program Modmath can be used to do most of these calculations. This is the opening screen you see when you load the program called Modmath. And here's the menu. It has 7 different choices. We're first going to look at decimal numbers to mod numbers. So we have to choose a decimal number to start with, and I think I'll choose the number, let's say 26. And now we're going to have to select a mod number to go with that, so let's choose mod 12. Okay, and now when you press enter, the calculator will say it's congruent to 2. So we use the word equals here. The menu now goes on. You go back to the menu and we're going to do a sum, 50 plus 34, one that we did earlier. And we're going to use mod 7 as we did before. So I'm going to enter mod 7 here. Alright, now let's see what that's equal to. 50 plus 34 mod 7 equals 0. We can also add numbers in mod sets, and let's choose a modulus, let's say 13. Let's imagine a clock with 13 positions on it now. And so the first number I'm going to choose will be, let's say, 12. And the second number I'm going to choose will be, let's say, let's make it 9. So imagine on a clock which had 13 positions, and you did this. The arrow should point to 8 when you finish, and I'll let you verify this. Now let's solve that same equation that we solved earlier. Modulus 4, the expression was 5x minus 3 on the left hand side, and on the right of the equal sign was 7. Now we're going to ask the calculator to solve it, starting from 1 in its minimum domain and 30 for the maximum domain, and it starts locating the numbers 2, 6, 10, and so on. You see the arithmetic sequence developing, which will be characteristic of all modular solutions for equations. And finally, after it reaches 30, we see the full solution set for our equation.